Today we will be doing 1.2, finding limits graphically and numerically. We are going to Alright, so today we are going to push it to the limit. So in mathematics, a limit is a value that a function approaches as the input or index approach some value. So it's basically just whatever value we are approaching. This is a little bit of a more formal definition. If f of x, if a function becomes arbitrarily close to a single number L as x approaches c from either side, then the limit of f of x as x approaches c is L. And it is written like this. The limit as x approaches some value c is L. So practically all that this is saying is if we have this like graph here, it's saying what's the limit of f of x as x approaches 1? Well, if we look at where we're at 1, this graph actually has a hole here at 1. There's not actually a point, but we see that the graph is getting close there on either side. And so the limit as x approaches 1 of f of x is actually 3, because we're actually right there at 3. It's just basically saying where are we at on our graph, even if that point isn't there, where is it approaching from both sides? Another way that we can solve this is to use a table. We're looking at where's the limit, where is it going from on both sides, and so we could use this table here. We have the limit as x approaches 2, so it's saying let's plug in all of the values close to it and see if they line up. I set my calculator somewhere. Let me find it really quick. Here it is. Sorry about that, guys. So let's type this in. So we're going to just type it into the graph. X squared, let's put parentheses though since this one's a fraction. X squared minus 3x plus 2 all over x minus 2. And so this time though, we're going to switch it to table mode. Second table, you may have to adjust your mode so that you can include table values. If not though, just go straight to table and we're going to type in these values: 1.75, 1.9, 1.99, 1.999. So what we're doing is we're getting close to this value of 2. It wants us to find the limit as x approaches 2, which, see, it gives us an error. So maybe like that last graph, we have a hole there. And so we're trying to estimate what's actually going on here. What's happening as we get closer? So we see 0.75, 0.9, 0.99, 0.999, nothing. And then we have 1.001, 1.01, 1.1, 1.25. But as you can see, as we're getting closer to this value, these values are getting close to each other. So what could you predict would be between 0.99 and 1.001? It would be 1. It's right in the middle there. So the limit as x approaches 2 of x squared minus 3x plus 2 over x minus 2 is actually 1. We could look at the graph as well. Let's take a look here and see what's actually happening. So we have this line, and there's actually a hole there. If we trace it, we can see exactly as we thought. We're getting close to 1 and we jump right over it. So yep, that's exactly perfect because from both sides it's getting closer to that 1. So this one wants us to also use a table, but it didn't give us our boundaries. We're trying to get to 0 though. So we know we want that 0 in the middle of our table that we're going to plug into our function. So we just need to think about what's a little bit bigger than 0 and what's a little bit smaller than 0. We want to get just a little bit. So I'm going to do 0.001 and negative 0.001, and then we'll go 0.01, negative 0.01, and 0.1, negative 0.1. So I'm just trying to see what's happening on either side here. And then I'm just going to plug it in. If you forgot how to do your absolute value, it's math, number, if you hit over to the number, absolute value. So x over x, let's go to our table. And let's plug it in. Negative 0.1, negative 0.01, negative 0.001, 0, 0.001, 0.01, and 0.1. Okay, what the heck is going on here? So we have negative 1 on one side and we have 1 on the other side. So this one's a little bit different here. We need to be thinking, are these approaching the same thing? They're not. Let's look at our graph just to understand this a little bit more. So at 0, we've got this split here. So this limit is not approaching the same thing from the left and the right. So this one actually does not exist. And you can use this DNE to symbolize that if you don't want to write out does not exist. Because as we're coming from the left and the right, it doesn't line up. And we can see that this is our graph here as well. So this one does not exist. Let's take a look here. This one, it gives us the graph for us, and it's just asking for the limit. As we see here, though, from the left and from the right, we're not at the same point. Even though these are both like approaching infinity at 0, we're not close enough to do anything. They're like that one's not going to be the same limit because it's not the same on both sides. Okay, this one we do need to graph. Find sine of 1 over x. 1 over x. There we go. So let's go ahead and do a table. This one is also 0, so we can use this same form of table here. Oh my. So we get this, and then we get this error. This is a sine function, though. Let's take a look at our graph and get a better idea of what's going on. Whoa, that's messy. So this is actually, if we zoom in closer to 0, because we want to know what's going on at 0, maybe we can see what's happening from the left and the right if they approach the same thing. We actually have this oscillating function. And so what that means is that this is actually just going like this, right around 0. And unfortunately, as we get closer to 0, it's not getting there. And the reason being is that our sine function, it oscillates between 1 and negative 1. So it's just going like this. So this is another case of it not existing. So I just kind of want to wrap it up here with there are common types of behavior associated with non-existence of a limit. So when it doesn't exist. So if the function approaches a different number from the right side than from the left side, the limit does not exist. If it increases or decreases without bound as x approaches c. So that would be like this example here. It has no boundaries there. It's increasing or decreasing there. And the other one is that it oscillates between two fixed values. So that would be like our typical sine or cosine functions that could do that. Not necessarily will, but depending at what point you're at, it could if we have that sine of 1 over x or something like that. So those are your three major ones where it would not exist. Okay, let's talk about the formal definition of a limit. If you are confused by this, it's really okay. I don't want you to get caught up in the vocabulary, but it is important to be aware of this. What this is, so this is like the formal definition of a limit. Let f be a function defined on an open interval containing c, and let L be a real number. So this, we know what this means. As x approaches some number on our function, that's where our limit is. As x approaches this number, this is our limit because it's approaching it from the left and the right, just like what we were talking about. So what that means is that for every epsilon greater than 0, any number that you plug in down here, any number that you plug in for x, there exists a delta greater than 0 such that this function. So basically all that this is saying is that anytime we plug something in around this limit, it's going to line up. Then the distance between f of x and L is less than epsilon. So if I plug in a number a little bit bigger than this limit, I'm going to get right here. If I plug in a number a little bit smaller than the limit, I'm going to get right there. So again, I don't want you to get tripped up on this. This isn't something that you really need to like hardcore understand. As long as you are understanding the gist of what limits are and when they do not exist, you're going to be good. But I did want to expose you to the formal definition of a limit. Thanks, guys.